Let's talk quickly about venous drainage of the brain. So I'd like you, if you have it handy, just to get Gray's Anatomy for students and pull it up to pages 886 and 887. So 886, 887. So I'm going to sort of talk you through the process of blood drainage from the cerebrum. So I'd like to turn your attention up towards this top left image. What you can see is that here is a cerebral vein. The cerebral vein will be draining blood from the white matter in the cerebral cortex. It will be draining that blood into these bridging veins that you can see here, and the bridging veins will cross through the subarachnoid space and the subdural space, and then they will empty into these, and this is one of the dural venous sinuses. And so this one that you can see here, so here's the falx cerebri, this one's in the midline, and this is the superior sagittal sinus that you can see here. So this is actually embedded within the falx cerebri. And so you may be thinking, well, hang on a minute, this is a bit weird. What we're seeing here is actually venous channels, but they're embedded in dura. I haven't seen that before. Why would we have that? Well, it's actually very clever. So these dural venous sinuses that you can see here are actually lined by endothelium, which you know is the same type of epithelium lining any other blood vessel in the body, or a lymphatic vessel, or the heart, the chambers of the heart for that matter. And the only difference is that the dura has a thick, non-distensible wall, whereas a normal vein would have a thin, distensible wall. And if you think about it, this makes sense, because in the brain, if we had normal veins here, then they would be distensible. So if there was a lot of blood suddenly being returned, so if there was a higher metabolic rate occurring in your cerebrum, getting higher amounts of blood to it, higher amounts of blood returned, then what would happen is that if we had normal veins here, then they'd start to dilate. And this is not a good thing. Why? Because if you had dilation, you get increased volume. And if you get increased volume, you raise the pressure within the closed cranial cavity. And this can quickly lead to things like coma and compressive effects on the cerebrum, which is not good for us at all. So that's why we have our venous channels embedded within dura, because then they are non-distensible structures. So, superior sagittal sinus, you can see there. Superior sagittal sinus is going to go down to at the level of the internal occipital protuberance, which is where we've cut through this transverse section. You can see that we have a sinus here, and this is the confluence of sinuses. So this is where the superior sagittal sinus and the inferior sagittal and straight sinus are all going to meet. So superior sagittal sinus here and straight sinus here, carrying blood from the inferior sagittal sinus. That sort of makes sense. Superior sagittal sinus is in the sagittal plane. Okay, it's a venous sinus. Inferior sagittal makes sense. It's inferior and it's sagittal. And straight because it's straight. Right, down to the confluence of sinuses, which is just here. Then this moves on to the transverse sinuses, which you can see here. And you would have seen from last week that we actually have grooves in the squamous portion of the occipital bone, and those grooves are made by these transverse sinuses. And then we have a sigmoid sinus that you can see here, which forms the sigmoid groove in the occipital bone. And then what happens is that inferior to the sigmoid sinus is going to turn into the internal jugular vein. Where does this happen? Where does this transition happen? At the jugular foramen. So this is why it's called the jugular foramen, because the sigmoid sinus drains into the internal jugular vein. So if I was to ask you a question about what is the major vein that drains, that's present in the neck and drains the whole of the internal cranial cavity, then you would have to answer the internal jugular vein.